Hi students, how are you? I'm fine. I hope you also fine. Take care of your health. Be positive in your life. Daily spend some time in your favorite temple to get positive energy. Don't spend so much of time on phone for unnecessary things. Use technology to learn knowledge. Now coming back to our third class in this chapter, dielectrics and magnetic materials. In this video, we will discuss three fundamental properties of dielectric materials. 1. Polarizability is denoted by alpha, a microscopic property of individual atoms and molecules. 2. Electric susceptibility is denoted by chi sub e, a macroscopic property of the bulk material. 3. Dielectric constant is denoted by epsilon sub r, a macroscopic ratio that connects to capacitance and electric field reduction. These three quantities completely describe the dielectric behavior of any material. They are interconnected. Understanding one helps you understand all three. Together, they bridge the gap from single atom physics to bulk material engineering. Why these matter? In any GATE, CSIR net, JEE exams and other competitive exams, question on dielectrics you must know. A. What each quantity means physically. B. The defining formula. C. The units. And D. How they connect to each other. This class covers all of these with full derivations. Now we will discuss first property, dielectric polarizability. When you apply electric field to the material, what happens at the atomic level? From previous class, that is in video 2, we know that when an external electric field E is applied to a dielectric material, each atom develops an induced dipole moment mu. The positive nucleus shifts slightly in the direction of E. The negative electron cloud shifts slightly opposite to E. This creates a tiny separation of charge centers within each atom. The natural question arises, how easily does a given atom get polarized? Different atoms respond differently to the same electric field. Helium hardly shifts, that is, helium is hard to polarize due to its two electrons being tightly bound to the nucleus, its atomic number Z equals 2. Whereas in cesium, charges shifts a lot on applying electric field. Cesium atomic number Z equals 55. It is one of the most highly polarizable neutral atoms in the periodic table. This is due to its position as an alkali metal with a single valence electron in a far from nucleus reaching 6s shell. So we need a quantity to measure this easiness. That quantity is polarizability alpha. Definition of polarizability. Polarizability is defined through the relation between the induced dipole moment of a single atom and the local electric field acting on that atom. Defining relation mathematically. Induced dipole moment mu is directly proportional to applied electric field E. Then mu equals alpha E, where alpha is proportionality constant called as polarizability of atom. Where mu is induced dipole moment of the single atom, units are coulombs meters. Alpha equals polarizability of the atom. Units are farads times meter squared. E equals local electric field acting on the atom in volts per meter. This is a linear relationship. Doubling the field doubles the dipole moment. The proportionality constant alpha is what we call polarizability. Important note, here electric field E is the local field at the atom's position, not necessarily the total external applied field. In dense materials, the local field differs from the applied field due to contributions from surrounding dipoles. This distinction becomes important in advanced topics like the Clausius-Mossotti relation. Now we will see the derivation of the units of alpha. Units of alpha are farad meter squared. Starting from the defining relation, we solve for alpha. Step-by-step unit derivation. Alpha equals mu over E. Unit of induced dipole moment. Mu equals coulomb times meter. Unit of electric field. E equals volt per meter. Therefore, alpha equals C times m over volt per meter equals C times m times meter per volt equals C times meter squared over V equals C times meter squared times volts to the power of minus 1. Now recall that farad equals coulomb per volt. So C over V equals F. Substituting back, alpha equals F times m squared. Final answer, unit of alpha equals F times m squared, farad meter squared, also written as farad times meter squared or coulombs times meter squared times volts to the power of minus 1. Now we will see physical meaning of polarizability is atomic capacitance. The unit farad times meter squared is revealing. The farad is the unit of capacitance, the ability to store charge under voltage. So polarizability is essentially atomic capacitance. It measures how much charge displacement, storage, an atom can handle. For a given amount of electrical pressure, voltage per field. A high alpha means the atom is a good capacitor at the atomic scale. Let us see example of polarizability. Let us consider spring example. Springs of different stiffness. Imagine two springs, one soft and one hard. Apply the same force to both. Soft spring will stretches more and leads to large displacement. This is like an atom with large alpha, which is easy to polarize. Example, cesium. Large atoms with loosely bound outer electrons. By applying same force, hard spring will stretches less, that leads to small displacement. This is like an atom with small alpha, which is hard to polarize. Example, helium. Small atom with tightly bound electrons. The spring constant of the atom is the restoring force that pulls the electron cloud back to its equilibrium position. Larger atoms with more loosely held electrons have weaker restoring forces, leads to higher alpha. Next we will see factors affecting polarizability. Atomic size. Larger atoms have electrons farther from the nucleus, leads to weaker binding, leads to higher alpha. Number of electrons. More electrons equals bigger, more deformable electron cloud, leads to higher alpha. Type of bonding. Ionic and polar molecules often have higher alpha than covalent non-polar molecules. Electronic configuration. Noble gases have very low alpha. Closed shells are hard to deform. Let us see polarizabilities of different atoms. Helium, very hard to polarize. Neon, hard to polarize. Argon, moderate to polarize. Easy, permanent plus induced to polarize. Cesium, very easy to polarize. Next, sodium chloride, ionic, high polarizability. Next we will discuss microscopic versus macroscopic property. This is a crucial conceptual point for exams. Alpha is microscopic, property of a single atom or molecule. P is macroscopic, property of the whole material. Connection between polarizability alpha and polarization P. Consider a dielectric with n atoms per unit volume. Each atom has induced dipole moment. Mu equals alpha E. Total dipole moment per unit volume equals polarization. P equals n times mu. Then P equals n times alpha E. This is relation between P and alpha. We can also express mu equals P over n. This gives the average dipole moment per atom from the macroscopic polarization. Next we will discuss about electric susceptibility, chi sub E. Polarizability alpha tells us about a single atom. But in engineering and physics, we usually work with bulk materials. We need a quantity that tells us how responsive is the material as a whole to getting polarized. This quantity is the electric susceptibility. It is denoted by chi sub E. Definition: chi sub E equals P over epsilon naught E, where P equals polarization of the material, coulombs per square meter. Epsilon naught is permittivity of free space, is equal to 8.854 times 10 to the power of minus 12 farads per meter. E represents applied electric field, volts per meter. Rearranging, P equals chi sub E epsilon 0 E. This is one of the most important equations in dielectric theory. There are no units for electric susceptibility. Prove that chi sub E is dimensionless. According to dimensional analysis, chi sub E equals P over epsilon naught E. Dimension of P equals C over m squared equals C times m to the power of minus 2. Dimension of epsilon naught equals F over m equals C squared times S squared times kilogram to the power of minus 1 times meter to the power of minus 3. Dimension of E equals V over m equals kilogram meter second to the power of minus 3 ampere to the power of minus 1. We will get both numerator and denominator equal values, that is coulomb meter to the power of minus 2 over coulomb meter to the power of minus 2. It implies electric susceptibility doesn't have units or dimensionless quantity. Simpler or another approach to prove electric susceptibility has no units is epsilon naught E has units of F over m times V over m equals C over V times V over m squared equals C over m squared. P also has units C per square meter. Therefore, chi sub E equals C over m squared divided by C over m squared equals dimensionless, no units. Next, derivation. Connecting chi sub E to alpha. This derivation shows how the macroscopic chi sub E emerges from the microscopic alpha. Starting equations. We know P equals N alpha E is equation 1. From definition of polarization, P equals chi sub E epsilon naught E is equation 2. Equating 1 and 2. N alpha E equals chi sub epsilon naught E. Cancelling E from both sides where E is not equal to 0, then we will get N alpha equals chi sub E epsilon naught. Solving for chi sub E. Chi sub E equals N alpha over epsilon naught. This is the key bridge equation. It connects the microscopic property alpha, the single atom, to the macroscopic property chi sub E, the bulk material, through the number density N, atoms per unit volume. Now we will discuss physical interpretation of electric susceptibility. A large chi sub E means the material is highly responsive to electric fields, it polarizes easily. A small chi sub E means the material barely responds, it's hard to polarize. Chi sub E is always positive for dielectrics since P is always in the direction of E for linear dielectrics. Next we will see some materials, their approximate electric susceptibility values and their interpretation. Water, H2O, having electric susceptibility values approximately 79. That is, it is extremely responsive, polarizes very easily. Glass, 4 to 10, moderately responsive. Diamond, approximately 4.7, moderate. Paper, 2 to 4, low to moderate polarizability. Air, approximately 0.0006, hard to polarizes. Vacuum, 0, no material, no polarization. Let us solve one problem. Example, a dielectric has polarization P equals 4.0 times 10 to the power of minus 6 coulombs per square meter, when an electric field E equals 500 volts per meter is applied. Find chi sub E. Solution. Chi sub E equals P over epsilon naught. E equals 4.0 times 10 to the power of minus 6 divided by 8.854 times 10 to the power of minus 12 times 500 equals 4.0 times 10 to the power of minus 6 divided by 4.427 times 10 to the power of minus 9 equals 903.5. Answer. Chi sub E is approximately equal to 903.5. This is a very high susceptibility. The material is highly polarizable, like ferroelectric ceramics. Next we will discuss about dielectric constant epsilon sub r. Definition. The dielectric constant, also called relative permittivity, is defined as defining relation epsilon r equals epsilon over epsilon naught, where epsilon equals absolute permittivity of the material farads per meter, epsilon naught equals permittivity of free space equals 8.854 times 10 to the minus 12 farads per meter. It is the ratio of commutativity of the material to permittivity of free space. It is dimensionless. Physical meaning of dielectric constant is field reduction factor. Epsilon r tells us by what factor the electric field is reduced inside the dielectric compared to vacuum. Example, if epsilon sub r equals 5, it implies the field inside the dielectric equals 1/5 of the vacuum field. That is, the material shields 80% of the external field and the capacitance is multiplied by 5. Now, the derivation epsilon r from field reduction. When a dielectric is placed in an external field E0, the polarization of the material creates an internal opposing field EP from induced surface charges. The net field inside becomes net field inside dielectric E equals E0 minus EP, where E0 equals original applied field. EP equals field due to polarization induced surface charges. The polarization creates surface charge density, charge per unit area, sigma p, and E sub p equals sigma sub p over epsilon naught equals P over epsilon naught. Substituting, E equals E naught minus P over epsilon naught, but P equals chi sub E epsilon naught E. So, E equals E0 minus chi sub E epsilon naught E over epsilon naught. E equals E naught minus chi sub E plus chi sub E equals E naught E of 1 plus chi sub E equals E naught slash E equals 1 plus chi sub E. But epsilon sub r equals E naught over E by definition as the field reduction factor. So epsilon sub r equals 1 plus chi sub E. This is a fundamental relation in dielectric theory. Next, capacitance with dielectric capacitance of a capacitor C equals epsilon r C0. Here C0 equals epsilon 0A over D. Capacitance of a parallel plate capacitor without a dielectric and C equals epsilon A over D equals epsilon r epsilon 0. A over D equals epsilon r times epsilon 0A over D. Capacitance of a parallel plate capacitor with dielectric permittivity epsilon equals epsilon r epsilon 0, filling the gap. Here C equals epsilon r C0 means the capacitance increases by a factor of epsilon r. This is why dielectrics are used in capacitors. They multiply the storage capacity. The next topic is Gauss's law in dielectrics. Gauss's law, vacuum, integral over E dot dA equals Q over epsilon naught. Gauss's law with dielectric, the integral of E dot dA equals Q over epsilon equals Q over epsilon r epsilon naught. For a parallel plate capacitor with surface charge density sigma, E equals sigma over epsilon equals sigma over epsilon r epsilon naught. Compare with vacuum, E naught equals sigma over epsilon naught. So, E equals E naught over epsilon r. The field is reduced by a factor epsilon sub r. Why dielectric constant epsilon sub r greater than or equal to 1 always? Proof. We know that epsilon sub r equals 1 plus chi sub E. Since chi sub E greater than or equal to 0 for all dielectric materials, polarization always opposes the applied field for linear dielectrics. So, epsilon r equals 1 plus something greater than or equal to 0, greater than or equal to 1. Epsilon r equals 1 for vacuum. Chi E equals 0, no material. Epsilon r greater than 1 for all real dielectrics. Also, since E equals E0 over epsilon r and E less than or equal to E0, field can only decrease, not increase inside dielectric. We again get epsilon r greater than or equal to 1. Next, the important parameter electric displacement vector D. The displacement vector D simplifies dealing with dielectrics by absorbing the polarization effect. Defining relation D equals epsilon naught E plus P. Since P equals chi E epsilon naught E, D equals epsilon naught E plus chi E epsilon naught E. D equals epsilon naught E 1 plus chi E. D equals epsilon naught epsilon R. E. D equals epsilon E. Key point. D depends only on free charges, while E depends on both free and bound polarization charges. This makes D much easier to use in Gauss's law for dielectrics. Typical epsilon R. Values of some materials. Vacuum 1 exact. Reference value. Air 1.0006. Barely different from vacuum. Teflon PTFE 2.1. Low. Used in cables. Paper 3 to 5. Moderate. Glass 5 to 10. Moderate high. Mica 5 to 7. Good capacitor dielectric. Silicon Si 11.7. Semiconductor substrate. Water H2O approximately 80. Very high. Polar molecule. BaTiO3 1200 to 10,000. Ferroelectric extremely high. SrTiO3 approximately 300. Paraelectric ceramic. Solved example. Example. A parallel plate capacitor has C0 equals 10 picofarads. A mica sheet epsilon sub r equals 5.4 is inserted. Find A. New capacitance. B. Chi sub E of mica. Solution. A. New capacitance. C equals epsilon sub r times C0 equals 5.4 times 10 equals 54 picofarads implies 5.4 times more storage. This is why dielectrics are used in capacitors. B. Susceptibility of mica. Chi sub E equals epsilon sub r minus 1 equals 5.4 minus 1 equals 4.4 implies dimensionless as expected. Master summary of this class. Now see the three properties comparison table. According to a scale, polarizability alpha is microscopic, is related to a single atom, susceptibility JEE is related to macroscopic, bulk material, and dielectric constant epsilon r is a macroscopic property, bulk. The definition of polarizability alpha is the ease of polarizing one atom. Definition of susceptibility JEE, responsiveness of the material to an applied electric field. Dielectric constant epsilon r is defined as the field reduction factor. Formulae: mu equals alpha E, JEE equals P over epsilon naught E, epsilon r equals epsilon over epsilon naught. Unit of alpha is force meter squared. Units of JEE, epsilon r are dimensionless, and see all differences. In the next class, we will discuss very important topics in detail. The derivation of the electric displacement vector D and types of polarizations present in dielectric materials. Thank you for your support. Keep watching these videos, like, share and subscribe.